Good evening. My name is Satyendra Singh, and today I am presenting my dissertation. My dissertation title is Detecting Fraudulent Transactions in Digital Banking Using Predictive Analytics. This research was conducted as a part of my MSc in Data Science at Liverpool John Morris University. The objective of this study is to design, evaluate machine learning module for fraud detection in highly imbalanced digital banking dataset. Now, today I will briefly discuss the background and problem statement, which followed by the research aim and objective. Then I will cover the literature review, research methodology, results and evolution, and finally conclude with future research directions. Digital banking has transformed financial services significantly. However, the exponential growth in transaction volume has increased vulnerability to fraud. Fraud patterns are becoming more complex and adaptive. Traditional rule-based systems struggle to detect evolving fraud patterns. Therefore, intelligent predictive systems are required to proactive fraud detections. Fraudulent transactions represent less than 1% of total transactions. This creates severe class imbalance. High false positive rates affect customer experience and operation efficiency. Accuracy alone becomes misleading in highly imbalanced dataset. Additionally, fraud detection system must support real-time analysis and regulatory interpretability. The main aim of this research is to design and evaluate a machine learning based fraud detection framework. And the objective include analyzing fraud behavior patterns, addressing class imbalance, implementing random forest MLP cat boost models, and evaluating them using imbalance sensitive performance metrics. This study contributes by reducing financial losses caused by fraud. It improves detection reliability by balancing precision and recall. It also supports regulatory transparency through model interpretability. Instead of focus only on accuracy, this study emphasizes business relevant evaluation metrics. The dataset used is the Kaggle credit card fraud dataset. It contains 2,84,807 transactions, of which only 792 are fraudulent. The features are PCR transformed for confidently. The dataset is highly imbalanced with only 0.17 fraud cases. This makes it suitable for evaluating fraud detection model under real-world imbalance conditions. Existing studies show that random forest is widely adopted as a strong baseline model. XGBoost achieves high ROC-AOC performance. SMART is commonly used to address class imbalance. However, many studies overemphasize accuracy. Deep learning models such as CNN and LSTM capture nonlinear patterns. Hybrid DNA autocoder models have also been explored. Federated learning enable privacy-aware systems. However, research gaps include limited interpretability, lack of statistical validation, and limited structure comparative evaluation. This study addresses these all gaps. This study follows a quantitative comparative framework. It uses supervised classification techniques. All experiments were conducted in an offline controlled environment to ensure consistent comparison. Random forest was selected as a robust assemble baseline which feature importance capability. MLP was chosen to capture non-linear fraud patterns. NetBoost was selected due to its gradient boosting efficiency, ability to handle complex feature interactions, and reduced overfitting through ordered boosting. Models were evaluated using precision recall and F1 score, ROC AOC, and PR AOC were also calculated. Additionally, KS test and Wells-T test were used for statistical validation. Error analysis was performed to assess false positives and false negatives. Now, all models achieved above 98% accuracy. However, accuracy was not considered the primary metric due to class imbalance. CatBoost achieved a ROC-AOC of 0.9847 and demonstrated strong precision recall balance. It also reduced type 1 errors, meaning false positives. In imbalanced datasets, the precision recall curve provides better insight than ROC. CatBoost showed superior minority class detection capability. This confirms it's suitable for fraud detection tasks. The KS test confirmed effective class separation. The Wells-T test validated statistical significance between model performance. Assemble methods were statistically superior to stand-alone neural models. The research objectives were successfully achieved. Assemble model outperformed stand-alone models. CatBoost demonstrated the best overall performance. Handling class imbalance is essential for reliable fraud detection systems. Now, future work can focus on real-time integration of the model into banking system. Explainable AI techniques can enhance regulatory transparency. Advanced deep learning architectures may further improve detection accuracy. Cross-institutional dataset validation is also recommended. Now, this research is supported by peer-reviewed academic studies in fraud detection and predictive analytics. Thank you so much.